Hello everyone. In this video, I'm going to show you how to solve problems concerning the principles of direct current generators and motors. Let's start with problem number 1. A 6-pole DC generator has an armature winding with 504 conductors connected in 6 parallel paths. Calculate the generated voltage in this machine if each pole produces 1.65 times 10 raised to 6 Maxwells and the armature speed is 1,800 revolutions per minute. In solving problems like this, it's always advisable to enumerate or list down the given parameters. So in enumerating the given parameters, we have the number of pole, which is equal to 6, the number of conductors, which is equal to 504, the number of parallel paths, which is equal to 6. The flux per pole is also given to be 1.65 times 10 raised to 6 Maxwells, and the armature speed is 1,800 RPM. Right? Now, we already list down the given parameters. Now, we list down the requirements of the problem. And based on the problem, we are required to calculate the generated voltage in this machine. And the generated voltage is given by the equation pole times the flux per pole multiplied by the speed of the machine times the number of conductors all over 60 times A multiplied by 10 raised to negative 8. And the resulting unit of this would be volts. Now, we have to take note that the flux per pole must be in Maxwell's and the speed must be in RPM. So, if we're going to substitute the given parameters in this equation, we would now have Eg equals 6 multiplied by 1.65 times 10 raised to 6 multiplied by 1,800 multiplied by 504 conductors all over 60 multiplied by 6 times 10 raised to negative 8. So if we're going to bring out our calculator here, we will be having 6 multiplied by 1.65 times 10, right? So that would be times 10 raised to 6 multiplied by 1,800 multiplied by 504 multiplied by all over 60 times 6 times 10 raised to negative 8. And the answer is 249.48 volts. This is now the generated voltage of the generator with these given parameters. Problem number 2. Calculate the voltage generated by a 4-pole DC machine given the following particulars. The number of slots in the armature is equal to 55. The number of conductors per slot is equal to 4. Flux per pole is equal to 2.62 times 10 raised to 6 Maxwells. The speed is equal to 1,200 RPM. And the number of parallel paths is equal to 2. So, if we're going to enumerate or list down all the given, we have T equals 4, and then the slot or the number of slots in the armature is equal to 55. The number of conductors, or that Z over S, is equal to 4. The flux per pole is given to be 2.62 times 10 raised to 6 Maxwells. The speed is given to be 1,200 RPM, and the number of parallel paths is equal to 2. So, we are required to calculate the voltage generated of this machine with this given particulars. Now, the required is Eg, and it's equal to P, phi, N times Z all over 60 times A multiplied by 10 raised to negative 8, and this is in terms of volts. So if we're going to substitute the given parameters in this equation, we'll be having 4 multiplied by the flux per pole, so that's 2.62 times 10 raised to 6, multiplied by the speed, which is 1,200 RPM, multiplied by the number of conductors. But the number of conductor is not yet given. However, we can solve the number of conductor by multiplying the number of conductor per slot multiplied by the number of slots. So this would now be equal to 55 multiplied by 4, or I interchange it. So the number of conductor per slot is equal to 4, and then the number of slots is equal to 55. So the number of conductors uh, is equal to, right? So that's 55 times 4, so that's equal to 220 conductors. So if I'm going to substitute the number of conductors in here, all over 60 multiplied by the number of parallel path, which is equal to 2, times 10 raised to negative 8. So again, bringing out our calculator here, we'll be having 4 multiplied by 2.62 times 10 raised to 6 multiplied by 1,200 RPM times 220 all over 60 times 2. And this would be times 10 raised to negative 8. Alright, so the generated voltage of this machine is equal now to 230.56 volts. Problem number 3. A 4-pole machine generates 250 volts when operated at 1,500 RPM. If the flux per pole is 1.85 times 10 raised to 6 Maxwells, the number of armature slots is 45, and the armature winding has 2 parallel paths. Calculate the total number of conductors and the number of conductors in each slot. So if we're going to list down the given parameters here, we have number of poles is 4. The generated voltage is given to be 250 volts at speed of 1,500 RPM. The flux per pole is also given to be 1.85 times 10 raised to 6 Maxwells. The number of armature slots is equal to 45, and the armature winding has 2 parallel paths. So the required in the problem is the total number of conductors Z and the number of conductors in each slot. So since the generated voltage is given, we can use the formula Eg equals T phi n Z all over 60 times A times 10 raised to negative 8. The generated voltage is given, the number of poles is also given, the flux per pole is also given, the speed is given, A is also given, thus leaving us Z as the only unknown. So we can manipulate this one, right? So we can manipulate this one to solve for the formula or to derive the formula for the conductor. So if we're going to cross multiply the given equation, we'll be having Eg multiplied by 60 times A equals P multiplied by phi NZ multiplied by 10 raised to negative 8. And since we are interested in the number of conductors, we're going to divide both sides by P phi N and 10 raised to negative 8. Therefore, the total number of conductors will now be equal to the generated voltage multiplied by 60 times A all over P phi N times 10 raised to 8. So if we're going to substitute the given parameters, the generated voltage is equal to 250 volts, 60, the number of parallel paths is 2, all over P, which is 4 phi, or the flux per pole, which is 1.85 times 10 raised to 6, and we have the the speed, which is equal to 1,500. Right, so that's 1,500 multiplied by 10 raised to 8. So again, if we're going to bring out our calculator here, this would now be 250 times 60 times 2 all over, right? So that's 4 times 1.85 times 10 raised to 6 multiplied by 1,500 times 10 raised to positive 8. So the answer, or the total number of conductors, is 270.27, but since the total number of conductors must be an integer, so we're just going to round off the result. So this would be equal to 270 conductors. Right? And for letter B, we are required to determine the number of conductors in each slot. So to determine that, we're just going to multiply the total number of conductors with the total number of slots, and this would now be equal to 270 all over the total number of slot is 45, so that would be 270 divided by 45. Again, bringing out our calculator here, that would be 270 divided by 45. So the total number of conductors in each slot is equal to 6. Problem number 4. What is the frequency of the alternating voltage generated in the armature conductors of a 10-pole 500 RPM machine? So if we're going to list down the given in this problem, we have the number of poles, which is equal to 10, and the speed of the machine in RPM, which is 500 RPM. Now we are required to determine the frequency of the alternating voltage, okay? So the frequency of the alternating voltage can be computed by the formula P times the RPM over 120. And this is in terms of cycles per second, or basically in terms of hertz. So if we're going to apply the formula to solve the given problem, the frequency would now be equal to 10 multiplied by 500 all over 120. So the frequency is now equal to 10 times 500 divided by 120. So that would be 41.67 hertz. Problem number 5. At what speed is an armature rotating in a 12-pole machine if the frequency in the armature conductors is 50 cycles per second? So if we're going to list down the given in this problem, the frequency is given to be 50 cycles per second, or that is 50 hertz. The number of pole is 12, right? And we are required, right? So if we are required to determine the speed of the armature in the machine. And since the formula for the frequency of a machine is equal to P times N over 120, we can solve for N, which would now be equal to 120 times F over P. So if we're going to substitute the given F and P in this equation, we'll now have 120 multiplied by 50 all over 12. So bringing out our calculator here, this would now be 120 times 50 divided by 12, so that would now be equal to 500 RPM. This is now the speed of the machine at frequency 50 Hz. Problem number 6. Calculate the force exerted by each conductor 6 inches long on the armature of a DC motor when it carries a current of 90 amperes and lies in a field the density of which is 52,000 lines per square inch. So in this problem, the given are the length of the conductor, of each conductor, which is equal to 6 inches long, the armature, so this is a DC motor, the current that the conductor carries, which is equal to 90 amperes, and the field or the field density is equal to 52,000, right? So that's 52,000 lines per square inch. Now we are required to determine the force exerted by each conductor. And since the unit of the given parameters are in English system, we're going to use the formula beta times the current that's passing through each conductor, and then the length of each conductor all over 11,300,000. And the resulting unit of this would be in pounds. So if we're going to substitute the given parameters here, we would now be having 52,000 lines per square inches multiplied by the current, which is 90 amperes, and then the length, which is 6 inches, all over 11,300,000. So the force here, or the force exerted by each conductor, is now equal to 52,000 times 90 times 6 divided by 11,300,000. So that would now be equal to 2.48 pounds. This is now the force exerted by each conductor of the given DC motor. Problem number 7. What total current must the armature of a DC motor carry given the following information? Armature slots equals 72, conductors per slot equals 6, pole arcs cover 70.5% of circumference, flux density equals 58,000 lines per square inch, the armature core length is equal to 8 inches, the armature core diameter is equal to 21 inches, the number of parallel paths is equal to 6, and the torque exerted by the armature is 1,050 pound or foot-pound. So if we are going to list down the given here, the armature slot is equal to 72. The conductors per slot is equal to 6, and the pole arcs covers 70.5% of the circumference. The flux density is equal to 58,000 lines per square inch. The armature core length, right? So the armature core length is equal to 8 inches. The diameter of the armature core is equal to 21 inches. The number of parallel paths is equal to 6, and the torque exerted by the armature is 1,050 foot-pound. So we are required to determine, right? So we are required to determine the total current must the armature of a DC motor carry. So in here, we can use the formula for the force exerted by each conductor. However, the current that is used to compute for the force exerted by each conductor is only the current in one path. So if you would like to determine the total armature current, we are going to multiply the current that we are going to solve here by the number of parallel paths. Right? So in here, the torque exerted by the armature can be solved using the formula the force exerted by the armature multiplied by the radius of the armature core. Now, the force exerted by the armature can be computed by F, or the force exerted by each conductor, multiplied by the total number of conductors under pole faces. And we can solve for the force exerted by each conductor using the formula flux density multiplied by the current in the conductor times the length of each conductor all over 11,300,000 because the units of the given parameters are in English system. So, if we can solve for the current that is passing through each conductor here, and then we're going to multiply it by the number of parallel paths, that would now be the total current in the armature of a DC motor, right? So first, we're going to solve for FA because torque is given. The radius can be solved using this one because the diameter is 21 inch. Therefore, the radius of the armature is diameter divided by 2, so that's equal to 10.5 inches. So, FA, or the force exerted by the armature, is now equal to torque A all over R. So, this would now be equal to 1,050 foot-pound, right? So, that's 1,050 foot-pound all over 10.5 inches. But the units must be consistent, so we need to multiply this by 1 foot is to 12 inches. And if we're going to bring out our calculator here, we have 1050 all over 10.5 divided by 12. So that would now be equal to 1,200, or force A would now be equal to 1,200 pounds. Now, we are going to use this force exerted by the armature to solve for the force in each conductor. And the force in each conductor would now be equal to FA, or force exerted by the armature, divided by the total number of conductors directly under each pole faces. So the number of conductors can be solved with the given number of slots and the number of conductors in each slot. So the total number of conductors would now be equal 72 times 6, which is 432. So this is 432. And Z prime, because 70.5% is the number of conductors that is directly under the pole, we're going to multiply the total number of conductors by that percentage. So that is 0.705. So again, if we're going to multiply this by 0.705, the total number of conductors under each pole is 304.56. We just consider the decimal places because this is not yet the final answer. So that would be 304.56. So since Z prime is already solved, this is now equal to 1,200 pounds all over 304.56. So the force exerted by each conductor is now equal to 1,200 divided by 304.56. So this is 3.94 pounds. And we can already solve, or we can already use this force exerted by each conductor to determine the current that is passing through each conductor in each path. So if we're going to use F equals B, or flux density, times the current times the length of the armature all over 11,300,000, solving for I here, we would now have a formula which is now equal to I equals F multiplied by 11,300,000 all over the flux density multiplied by the length of the armature core. So this is now equal to 3.94 pounds multiplied by 11,300,000 all over the flux density, and the flux density is given to be 58,000 lines per square inch. So that's 58,000 lines per square inch multiplied by the length of the armature core, which is given to be 8 inches. So that would be 8 inches. So if we're going to bring out our calculator here, this would now be 3.94 times 11,300,000 divided by 58,000 times 8. So the resulting answer or the current is 95.95 amperes. Now, this is the current that is passing through one path. And to determine the total current that is passing or that is circulating in the armature, we're going to multiply this current with the total number of parallel paths. So this is now equal to 95.95 amperes multiplied by 6. So that's now equal to 95.95 times 6, 575.7 amperes. This is now the total current that is circulating in the armature conductors.